I would like to welcome all of you. This is our annual CITAC best paper in chemical metrology award series. Before going any further, I would like to share with you some basic information about very much. CITAC is an international organization advancing chemical measurement science since 1993. You can see we are 30 years old this year, so we are celebrating, getting to middle age. CITAC is the Cooperation on International Traceability in Analytical Chemistry, created in 1993 with a mission to improve traceability of chemical measurements everywhere in the world and ensure that analytical measurements made in different countries and at different times are comparable. We do this according to our values and ethical stances. Our practical objectives are to facilitate practical realization of metrological traceability in chemistry, to develop concepts that can be applied in analytical chemical laboratories, and to disseminate those concepts, to foster collaboration on metrology in chemistry internationally as a mean of effecting technology transfer and cost sharing, to promote metrological principles in chemistry through the development and guidelines and other tools for analytical chemical laboratories, to promote and harmonize quality practices in analytical laboratories, and to stimulate education and training on metrology in chemistry. So I would like to show with you. So this is our current lineup of leadership. You can see a very good international coverage from the Americas to Asia, and colleagues from Europe. Our membership are roughly evenly split between Europe, Asia, and Americas, with some representation from Oceania, Australia, and welcome Angelique from Africa. So new members, the organization is an open one, so members are welcome from all facets of chemical measurement science. About half of our members are from NMIs, or National Metrology Institutes, or designated institutes, having chemical metrology as their day job, but the other half is from academia, industries, and other fields where metrology and chemistry is either taught or practiced. So we we carry out our objectives primarily through the development of guidance documents, partially with EuroChem. You can see our latest set of guidance developed over the last few years. Over the years, there are about a dozen guidance documents have been co-developed with EuroChem. So some of these include, the latest one include EuroChem CITAC Guide on Assessment of Performance and Uncertainty in Qualitative Chemical Analysis. So this document is especially timely considering the JCG and VIM efforts on including terminology for qualitative analysis into our metrology guidance vocabulary. Use of uncertainty information in compliance assessment, metrological traceability in chemical measurements. This is the second edition of this. It's very important guidance, widely used guidance in chemical laboratories. And the fourth one developed in recent years is measurement uncertainty arising from sampling. So our other parallel organization which we collaborate with in guidance guidance development is the International Union of Pure and Applied Chemistry, which actually operates under the Analytical Chemistry Division, a subcommittee dedicated to metallurgy and chemistry. So there is a lively collaboration between CITAC and IUPAC in metallurgic-related matters. And two recent guidance, which I would like to highlight. The first one is Guide for Evaluation of Risk of Conformity Assessment of a Multi-Component Material or Object due to Measurement Uncertainty. And the second one is Classification, Modeling, and Quantification of Human Errors in Chemical Analytical Laboratory. So both of these, again, were co-developed by members of CITAC and IUPAC. So this is the two primary vehicles which we use, CITAC, IUPAC, and CITAC Eurochem collaboration for guidance development. The second approach to develop and promote metallurgical concept is organization of workshops. I would just like to highlight two recent ones. But there is a link on our website to all of our conferences and symposiums which we co-organized. I would like to share with you this. So the IUPAC, CITAC, Eurochem, and HSA a joint workshop on performance and uncertainty in qualitative chemical analysis. With the aim to assist laboratories using the recently mentioned Eurochem CITAC guide, Performance and Uncertainty in Qualitative Chemical Analysis. It was a 4-session event, very well attended, and I am highlighting this because the recordings are linked to our website. So if you head to our website, you can find the recordings on YouTube for this very interesting event. And our running series of conferences or symposiums or workshops organized as part of the Israel Analytica by our colleague Ilya Kesselman. The latest edition of this series took place January this year. The third main vehicle to develop and deliver our discipline building mandate in metallurgy and chemistry is the operation of and running of the CITAC Best Paper Award in metallurgy and chemistry. These are our winners from last year, and the online seminar which took place about a year ago in June, is also linked on our website, so you can find information on these. So without further ado, I would like to hand it over to Ricardo and let's get this symposium on the road. Thank you very much.
So let me briefly explain you the procedure for awarding the CITAC best papers. So like Zoltán already mentioned, so we aim at promoting the quality of chemical analysis, and one way of doing that is to highlight some relevant contributions to measurements in chemistry and biology that are published in peer-reviewed journals. And this awarding is coordinated by the CITAC vice chair. So the papers that will be presented in this session, the nomination was coordinated by Zoltán Mester, that was the CITAC vice chair last year. And then, so this procedure starts by the nominations done by CITAC members. So each CITAC member can nominate 3 papers, and they must justify the nomination by mentioning how relevant the papers are for improving the measurements capabilities in chemistry or biology. Then the nominated papers are assessed by the members, and they vote for the nominations, and then votes are collected, counted, and the 3 best scored papers are awarded best CITAC paper for that year. And we do not distinguish from these 3 which ones are the most voted ones. Then awarding certificates are issued, and then we have the chance to have these papers presented briefly in CITAC news and in the award ceremony. This is exactly what we are doing for the CITAC best paper from 2022. Since 2007, over 40 papers were awarded from 251 authors from 28 countries of 5 continents. So that's briefly how it works regarding the awarding the best CITAC papers. So the first paper that will be presented was published in Inductively Chemistry. The title is Primary Measurements of Gaseous Elemental Mercury Concentration with a Dynamic Range of 6 decades by Srivastava and Hodges. This work is both relevant for the relevance of measuring mercury contamination in gaseous samples, and also for the need to improve the measurements capabilities in this area. So let's have the presentation from Srivastava.
Well, I'd like to first thank CITAC for recognizing our paper on the metrology of on our paper on the metrology of mercury. In today's talk, I'll give a brief background of our traceability program at NIST and the more recent activity leading to its transition into the optical method as a primary measurement for gaseous elemental mercury mass concentration measurements. All our work is based on the elemental form, the gaseous elemental form. So for brevity, I'll refer it to as just mercury. The metrology of gaseous elemental mercury is critical to its regulation and compliance. Globally, more than 130 countries have now committed to reduce the anthropogenic emissions of mercury. In the US, the Environmental Protection Agency regulates source emissions from power plants. To aid with the compliance, in the US, the National Institute of Standards and Technology developed an SI-traceable certification program for mercury gas generators. These gas generators, as shown in the 2 cartoons, they are used for the calibration of continuous emission monitoring systems. And they work on the principle of dynamic dilution of a temperature-controlled mercury vapor source. Now, NIST maintains 2 prime generators to span the required emission regulation range. The NIST traceability framework, as defined by EPA, requires an unbroken chain of comparisons to the NIST primary standard, which is shown on the top. NIST certification program is aimed to implement this traceability framework. The primary generator output needs to be quantified and made traceable to the SI unit. And this was done through a method which was developed at NIST. Briefly, it starts with passive sampling using sorbent tubes, followed by sample processing using digestion techniques, and finally measurement using the isotope dilution cold vapor ICP-MS. To value assign the output, the analyzer response needs to be compared to known amounts of Mercury 3133 standard reference material. To address the throughput issues associated with this approach, we developed an optical method, which allows for direct and real-time sampling. Additionally, there is no usage of any reference material for any calibration. So how does this optical method work? It's based on the concept of laser absorption spectroscopy. So the laser absorption of a sample, in this case of mercury, gaseous elemental mercury, in a known path length is recorded using precisely stepped tunable laser in the region of absorption. The attenuation of light is given by the well-known Beer-Lambert's law. The experimental absorption coefficient spectra is then fitted using a spectroscopic model. The fitted spectrum area divided by the line intensity gives us the number density, which can then be easily translated into the mass concentration, which is what we are looking for. To do the spectroscopy, we take advantage of the well-characterized and high cross-section transition of gaseous elemental mercury in the UV at 253.73 nanometers. In our experiments, the x-axis is the frequency axis, which is scanned and measured at the megahertz level precision. The y-axis is derived from intensity measurements, which is at the 0.1% precision obtained using amplitude modulation techniques. The mercury spectrum which is observed is a linear combination of the individual isotope absorption coefficients. Now, mercury has 7 naturally occurring isotopes, and these combine to give the final spectra. Our first measurements were done on the saturated mercury vapor, which is shown here in a static cell, which is 1 centimeter in path length. We used our spectroscopic model to fit the data and obtain or derive the mass concentration leading to the vapor pressure. The derived concentrations were found to be in good agreement with the vapor pressure correlation equations developed by Huber, which are based on thermodynamic principles. Also consistent with the thermodynamic predictions, we observe good reproducibility across pressure and across buffer gas. So even though the shape changes, as you will notice in going from the left panel to the right panel, the fitted area stays the same, whether it's in absence of any buffer gas or in the presence of buffer gas. An additional point which came out through the study was a negative bias in the Dumouriez equation, which is an empirical vapor correlation equation, which is oftentimes used to predict the mercury generator set point value. And this will become important later on. Moving from the short static cell, we designed a setup to measure the mercury generator itself. We first started with a single pass cell, and in a more recent configuration, we have a dual flow cell approach, which allows us to make measurements across 6 decades of mass concentration. In this dual cell approach, we use a single pass cell as well as a multi-pass cell of known or measured path lengths. The setup allows for simultaneous sampling of the mercury generator output into the 2 cells, which have independent probes for the pressure and temperature and dedicated detectors for measuring the incident and transmitted intensities. The throughput of the system is pretty high. The scan time for a single spectrum is 10 seconds, and the 1/E sampling response time is less than a minute for the initial equilibration at a given set point. For our data treatment, we use a spectroscopic model, as I indicated earlier, which is based on first principles light matter interaction. The transmittance is described by the Beer-Lambert law and is expressed in terms of the absorption coefficient and the path length. The absorption coefficient can be further expanded into the number density, which is the unknown, the line intensity, and the line shape function. The line intensity is derived from lifetime measurements and is known from literature. The pressure and temperature dependent line shape is modeled using the Voigt line profile, which is found to give adequate fits to our data with residuals less than 0.2%. The fits then give us the unknown, which in this case is the number density. In applying the model to the experimental data, we seek to maximize the constraint on the parameters used. In other words, we try to fix them by independently first measuring them. So shown here is an example of a measurement of the collisional broadening coefficients. This is done by measuring the line broadening as a function of pressure conducted at a fixed mole concentration corresponding to a fixed output from the generator. In a similar fashion, we fix the path length parameters by independently measuring them. For the case of the single pass cell, we use the NIST dimension metrology coordinate measuring machine to get its path length, which is close to a meter. The multi-pass cell optical path length is then referenced to the single pass cell path length by concurrently measuring the mass concentration from the generator at a given set point. The problem then effectively reduces to comparing the areas within the absorption coefficients obtained from the two cells. The path length scales with the relative areas. This process was completed for a range of pressures to get a pressure averaged path length from the multipass cell. And this is found to be consistent with the theoretical predictions at the 0.2% level. Moving on to some figures of merit for the spectrometer. The first one is the lower detection limit, which was obtained using an Allen variance analysis done on repeatability measurements at 2 different concentrations. This was done over a period of 3 hours. As you can see in the plots, the precision improves with the integration time, reaching the highest precision at a concentration of about 1 nanogram per meter cube. 1 nanogram per meter cube is important because this is oftentimes the value quoted for ambient level concentrations of gaseous elemental mercury in the atmosphere. The other figure of merit is the dynamic range. To obtain the dynamic range, we evaluate the relative precision across the measured mass concentrations. Shown here are 3 scenarios for the 2 flow cells, as well as the single point for the short static cell used for measuring the saturated mercury vapor. In observing the trends, we can identify an initial linear region at low concentrations, ending up with a roll-off at high concentrations, which comes due to higher optical depth. Once one reaches this point, one would want to switch to a shorter path length cell to maintain linearity and allow detection at higher concentrations. This will eventually lead us to the curve or to the point on the extreme right shown in the green for the short cell, which corresponds to the measurements on the saturated mercury vapor. The overall precision, as well as the lower detection limit, improves in moving to the left in this plot, or in other words, moving to the longer path length. In order to observe, or in order to understand the trends in the data points, we also conducted Monte Carlo simulations. And we get good agreement shown here as solid curves for the 3 cases. The Monte Carlo simulations are also useful for extrapolating to measure conditions beyond our measurement. Using the combination of the multi-pass cell for the lower detection limit and the single pass cell for the upper detection limit, we get a 6-decade range for the dynamic range in the measurement of the gaseous elemental mass concentration. The combined relative standard uncertainty in the regulated emission range comes out to be 0.5%. It has components from both the non-statistical as well as statistical. The biggest component comes from the non-statistical type B, which is related to the line intensity. The type A contributions come from the fit residuals, the path length, as well as the repeatability, which is related to the repeatability coming from the generator performance. In a prior study, we had also validated the mass spectrometry based method against the optical method. And we got good agreement between the 2 values within our measurement uncertainties. Contrasting the derivation of the analyte mass concentration in the 2 primary methods. In one case, in the mass spectrometry method, what is required is calibrating the analyte response, as I mentioned earlier, against the response of known amounts of a reference material. This makes it a primary ratio method. In the case of the optical method, we obtain the analyte concentrations directly from the fits without having to calibrate the response against a reference material. This makes it a primary direct method. So this is a subtle distinction between the 2 primary methods. The new method has allowed us to redefine the traceability framework. The NIST prime generators are now referenced against the spectroscopic model-based approach to obtain the value assignment using the optical method. The ease of use and the accuracy of the optical method allows us to frequently monitor the output of a Mercury generator. In addition to calibrating the generator set points, we can also assess the accuracy of the generator. The generator set point value is a predicted value which is based on the generator's mass flow rate, pressure, source temperature, and the vapor pressure correlation equation used to generate the value. So here's a collection of measurements done in the regulated emission range using both the cells, the multi-pass cell and the single pass cell. Overall, the generator set point tracks the measured mass concentration. However, in this particular example, we observed a negative bias in the generator set point relative to the measured mass concentration. We believe most of this negative bias comes from the usage of the Dumouriez vapor pressure equation, which I mentioned initially. The other inaccuracies could be related to the measurements of the pressure and the mass flow rate and the temperature in the commercial Mercury generator. To make the primary generator an independent standard in itself for SI traceability, NIST is also working on developing an accurate Mercury generator. Optically, some of the things we are working on are shown in this plot. We are trying to improve the sensitivity, stability, and the accuracy. As far as sensitivity goes, we have completed the project by introducing a multi-pass cell, which, as I mentioned, allows us to go over a wide dynamic range. The stability here refers to further improving the precision on the x-axis, which is the frequency axis, and the y-axis, which is the intensity axis. The frequency axis can be further stabilized by locking the frequency of the tunable laser to an external cavity. The intensity can be further stabilized by using feedback loop mechanisms. As far as the accuracy goes, as I mentioned, in our uncertainty budget, the biggest contribution is the type B, the non-statistical contribution coming from the line intensity. The line intensity is related to the lifetime, and we have plans to directly measure it in the lab. Both improving the stability and the accuracy will naturally improve the uncertainty. With a lower uncertainty, hopefully at the sub-per-mil level, we can extend this technique to isotope ratio measurements. With that, I've come to the end of my talk. We have introduced a laser absorption spectroscopy technique. It's a direct method without the usage of any reference materials. And it allows us to go from the very low ambient to the very source emission range. And as far as the future direction goes, optically, we are trying to implement ways to measure isotope ratio, as well as on the gas metrology side, improve the accuracy of the primary generator. So with that, I'd like to thank you. And if there are any questions, I'll be happy to address it.
Okay, thank you very much for your excellent presentation and for timekeeping.
Yeah, sure.
Okay, so now we have 5 minutes for questions. Do we have questions from participants related with this interesting research? Zoltán, please.
Very nice presentation, Abnish. Thank you. Thank you for sharing. I just have a quick question. So the isotope effect is for mercury through the vaporization could be sizable. Is it in the same, uncertainty regime range where it would affect your mass fraction calculations? So just the natural variation of mercury, isotopic composition.
You mean in the optical? You mean the isotope abundance?
So the variation, the natural fractionation of mercury from various sources. So is that an impactful in the uncertainty range where your measurements taking place, or not really?
Yeah, we did some modeling. We actually go in with the natural abundance levels, actually quoted by your we reference your work, which you actually measured the isotope abundance of 3133. And then we did some Monte Carlo simulations. The effect is very small as far as the isotope abundance goes, as shown in this plot on the overall uncertainty. But with higher precision, we should be able to measure the ratios for, say, the 202 and the 200 directly.
Fantastic. Thank you. Thank you very much.
Okay. Do we have more questions? So if not, can I ask you about, so what is your target? So it looks at, so you want to improve the measurement capabilities even further. What is your goal? Do we have a target or a maximum uncertainty that you want to achieve, or so?
Yeah, sure. I think if we can go sub-per-mil level, which is factor of another 10, for instance, we should be able to measure isotope abundance values with high precision. So we want to measure isotope abundance and ratios. And right now we are roughly, I would say, around 1 per mil level uncertainty. And so we'll need to improve it by a factor of 10. So that these precisions can be improved if we can stabilize, as I mentioned, the x-axis and the y-axis. And we have ways to do that. So that's our goal, to move into the isotope ratio.
Okay. So thank you very much for your contribution.
Oh, there's another question, yes.
Sorry. So where is the question?
So that was probably me, Bernd Güttler. I just wanted to look into this a little bit deeper, and I'm a little bit curious as to whether you can achieve a maximum accuracy, a minimum measurement uncertainty via a primary method or a primary ratio method. So if you have a direct primary method, then you are related to the absorption cross-section of the pure mercury, as I understand. So what do you think is more suitable for you? Where can you get further?
You know, we have at least within our measurement uncertainties, the absorption cross-section is related to the line intensity, which is related to the lifetime. And so right now we're using the literature lifetime, which is about 12 or 13 measurements, and we are using the weighted average value. And we get good agreement within the measurement uncertainties for, let's say, the saturated mercury vapor pressure, which is very well studied. We would like to reduce that uncertainty by directly measuring the lifetime, which will give us the line intensity, which will give us the cross-section. So that's where we are headed.
Okay. Yeah, thank you very much for this. I think that's a very important and very exciting research, and that really takes us to the limits where you can go to in case of gas analysis. So thank you very much for that.
Thank you so much. Yeah.
Okay.
So Zoltán.
So maybe just one more quick question, Abnish, if you don't mind. So
Yeah,
you
yeah.
are approaching the 3100 uncertainty regime. So are you considering that this method, if you actually get this about an order of magnitude improvement, would be the primary method to assign value to the 3100 you know, materials to the spectroscopic atomic spectroscopic standards?
Are you referring to the 3133?
Yeah.
Oh yeah, you mean the isotope abundance assigning
No,
values?
the mass fraction, the mercury mass fraction solution standards, you know, maintained by NIST, you know, based on gravimetry.
Oh, so these are not isotope abundance, right? These
No,
are just...
not for isotope abundance, but for
well, in theory, yes, we can, because we can use a similar approach, which is the isotope dilution, cold vapor approach. We can apply that interface. And in fact, I was trying to do that with the laser absorption spectroscopy. We can just, you know, just use the same approach of transferring from the SRM 313 solution into the gas phase and make these measurements. So we should be able to make those measurements directly. And we can do that now with the given uncertainties, and if we improve, we should be able to lower it.
Yeah, so
and I think
also...
we can go one step further, which is directly measure the isotope abundance.
Yeah, that's also very interesting to have an independent verification through your Beer-Lambert approach on gravimetric preparation of spectroscopic standard solutions. So yeah.
Thank you for bringing it up. Thanks.
Thank you.
Okay, so it looks that we should move forward. Yes. Yes. No more questions? I don't think so. Okay, thank you very much for your contribution, and congratulations for the award. And so keep improving.
Thanks.
Capabilities.
All right, thanks.
Okay.
Good morning, good afternoon, and good evening to everyone. My name is Felipe Lourenço from University of São Paulo, Brazil. And I would like to introduce you Professor Liu-Xin Feng. Professor Feng is a scientist in the Chemistry Metrology Division of the National Institute of Metrology from China. He's mainly engaged in chemical metrology research, including mass spectrometry, food safety, environmental and metabolomics studies. He has developed more than 30 CRMs, and he also has rich experience in coordinating and participating in CCQM comparisons. Also, he is the author of more than 50 papers published in academic journals. And now Professor Feng will present us one of his latest paper, absolute quantification of total hemoglobin in whole blood by HPLC isotope dilution, inductively coupled plasma mass spectrometry. So thank you very much, Professor Feng, and the floor is yours.
I'm Liu Xingfeng from Nîmes, China, and I'm very honored and pleased to get this award. My major is in element analysis. That means I'm from the inorganic laboratory from Nîmes, China. And the topic of this presentation is about absolute quantification of total hemoglobin by HPLC, isotope dilution SP mass. It looks like a measurement of macromoleculars, but actually it's just a measurement of element. As far as we know, HGB hemoglobin is a very important biomarker, and the total hemoglobin concentration is one of the most frequently measurement, and the accurate determination of it could provide very important clinical information. The statistics showed that it takes 237 million euros for hematology test every year, and for approximate 32 million tests. As a result, reproducible and reliable measurement of hemoglobin is of great essential. At present, at this moment, the most frequently used methods are these. The first one is based on the measurement of the determination of centimeter hemoglobin. We can just use the abbreviation of HICN method. This method is just can be traceable to a specific SCHS standard, and the shortcomings of this method is mainly the toxic disposal of potassium cyanide. And the other strategy is AHD method. It is just an improved version of HIC method, and however, it is easily disturbed due to light scattering. And the most important thing is that both of the two strategies cannot be traceable to SI unit. This is a molecular structure of this hemoglobin. We can see that it mainly contains 4 peptides. And the 4 peptides include 2 alpha and 2 beta peptide chains. And each peptide contains 2 sulfur molecules, 2 sulfur atoms. And the other important is each peptide chain contains 1 protoheme. That means each peptide also containing 1 iron atom. So we can see from the structure that HGB contains, each HGB molecule contains 4 iron atoms and 8 sulfur atoms. So since it contains element, if we can just use the elemental-based strategy to measure the macromoleculars, because the mole ratio of the element and the molecular is fixed. So if can we do by element, we can first see the left picture, the left part. This is a traditional protein quantification strategy based on peptides or amino acids-based isotope dilution. We can see in the complex matrix, such as the serum blood or some things, the metalloproteins or protein mixtures will need separation or enrichment first. And then we just use the peptide digestion or hydrolysis to a specific peptide or amino acid. And then at last, it can be traceable to SI unit. This strategy is very clear, accurate, and reliable, and can be traceable to SI unit. But the disadvantages of this strategy are mainly the limited enzymatic digestion efficiency and complicated pretreatments. Also, in some cases, the sensitivity is not enough. The right one is a strategy based on element analysis. We can see that the metalloproteins or proteins mixture in complex matrix after the separation, similarly, after separation and enrichment, we can just determine the sulfur or iron in the proteins. And in this way, the proteins can be measured just through the sulfur or iron elements. We can see a very obvious advantage of this strategy is that a very clear and short traceability chain and a relatively lower uncertainty, because as we know, the measurement of elements is much easier than that of the amino acid or peptide. And the sensitivity of some elements always are very sensitive. For example, the iron element or zinc or copper, and sometimes are very sensitive for ICP-MS. But as we know, every coin has two sides. The main disadvantage of this strategy is that we also just rely on the separation efficiency, because in this paper, the measurement is hemoglobin. It's a very high, with a high abundance in blood or serum. But for some, that very small or very low content proteins, maybe the separation is very difficult. And more importantly, the structure information we cannot get any structure information using this strategy. So in the metabolomics research or in our inorganic research, we won't want to just take the place of the left strategy. We won't want to take the place of the peptide or amino acid based strategy. We just use the elements strategy to supplement the peptide strategy and combine the advantages of the both strategies. Just a short description of the inorganic isotope dilution mass spectrometry. And it is a little different with the organic-based isotope dilution, actually, because for most elements, it have several isotopes. So after the spike of element spike was added to the sample, and after equilibration, we just can get the content of the measurement by measuring the ratio of the isotopes. The advantage of this inorganic-based strategy is that it can clearly traceable to SI unit and with small uncertainty. Actually, in our CCQM IWG workshop, most of the CCQM comparisons was finished by this IDMS strategy. And also many CRMs are studied by this one. And this is a work of our we previously finished, also use this strategy. The left one is a CCQM P5050.2. It's an oxytocin purity determination. And the right CCQM comparison is about insulin comparison. In both of the comparisons, we just use the inorganic-based strategy to determine the macromoleculars, and good results was appeared. Also, we use this strategy to develop the CRMs. This is amyloid beta is a biomarker of the Alzheimer's disease. So in this work, we just use the two strategies based on amino acid-based isotope dilution and element-based isotope dilution. Two strategies was used to certify the CRMs. In this work, similarly, in this paper, we also measured the hemoglobin with the two strategies. The first strategy is based on iron-based IDMS, and the other one is based on the sulfur IDMS, because hemoglobin contains both sulfur and iron. This is a work about the iron measurement. We can see clearly that the challenge of this strategy is that how can we simultaneously quantify the transferrin at HGB? Because as we know, transferrin is also a very important biomarker in human body, in blood. So at this moment, we just want to, if we can develop a measurement procedure to simultaneously determine the two markers. However, one of the tough challenges was the simultaneous quantification of the two measurements was a significant content difference in whole blood, because we can see that the concentration of HGB is more than 20 times larger than that of transferrin. But we cannot adjust the concentration of the spike in the online HPLC IDS-TP-MS procedure. But we can realize the simultaneous quantification by just adjust the flow rate of the spike. We can see from the figure that in the before 25 minutes, we just use a much lower flow rate of the iron spike solution. And after the transferrin was separated, we just improve the flow rate of the spike. And in this way, just in one HPLC procedure, the two measurements could be measured. This picture shows the linear range LOD and the CV of the two markers. Both of the two markers, we can see that in the normal human range, we can realize the quantification of the two markers. Other strategy is based on the sulfur. As we know, sulfur is another element that could be used for HGB determination. However, few reports about the quantification of HGB via sulfur, mainly because maybe the potential interference from other sulfur-containing proteins. We can see that from the picture that a very, very obvious peak was observed in the HPL in the picture. But as we know, the concentration of transferrin is much lower than the HGB. So this peak was not likely to be transferrin. In this way, to figure out this strange things, we use another iron, the IEC HPLC mass to distinguish the peak, because the molecular weights and the content of ALB maybe is a very potential interference, because both the molecular weight and the content of ALB and the HGB are very similar. So we just use the IEC strategy to figure out the interference. But unluckily, because the transferrin and the ALB, the retention time is much closer, and the interference of ALB is very, very huge, very, very obvious to transferrin. So in the sulfur-based IDMS strategy, we cannot simultaneously determine both of the two analytes. Only HGB could be determined. This is a linear range calibration curves of HGB via sulfur. The results of the sulfur-based and iron-based strategies are in good equivalence, and the iron-based strategy could realize simultaneously determination of the two of HGB and the transferrin. For the method validation strategy, we use a CRM from IRMM to validate our method. The we can see from this picture that it's very clear, it's very pure, because this CRM is a purified HGB sample. So only when we use it for the iron determination, only one peak was observed. It's from HGB. But when come to the sulfur measurement, we can see another very obvious peak was noticed. After we look at the certificate of the sample, we just find that another it means maybe a protection reagent which contains the sulfur, which contains the sulfate was in the sample. So this is just the ME from the buffer. It's not macromolecular, because also for the HPLC, we did not observe any other peaks except for HGB. And the certificate and the certified value of the CRMs was in good equivalence. Lastly, we just use the clinical method to compare the strategies with element-based strategy. You can see from the picture that the strategies based on element and the ICN are very significant correlations we get, and the coefficients is more than 0.9. Both of the two strategies based sulfur and I are good enough. For the uncertainty, this is a uncertainty budget of a typical isotope dilution strategy. But we should notice that the red label, the red color, is the main contribution of this HPLC, I mean the online or post-column isotope dilution. The first one is the ratio, because the ratio we need to calculate the peak. So the ratio, sometimes the uncertainty from the ratio measurement may be very obvious. And the second one is the flow rate of the spike. And we should notice that we should consider that the uncertainty from the loss, it means an analyte loss during sample preparation, because it's a post-column isotope dilution. So for the sample preparation procedures, the uncertainty we must consider. And the U separation is a peak integration, because in our when we deal with the data, we can see a very small tailing peak of the just very near to the HGB peak. So if we can, when we choose different integration point, with some slight difference was observed. So we just also consider the uncertainty from this process. Overall, the uncertainty of both of the iron-based and sulfur-based strategy are 0% and 2.2%. So we come to the conclusion. In this paper, we just realized absolute quantification of hemoglobin and transferring by iron-based and sulfur-based isotope dilution strategy. The result of the two strategies are in good equivalence, and the measurement results could be directly traceable to SI. And the most important is that this strategy can also be used for the quantification of other sulfur or iron-containing proteins in clinical area. But I must say that also shortcomings of this paper, of this work. The most one is the molecular, I mean, the high abundance molecular is apparent in this work. When we come to very small abundance macromolecular, maybe in the separation procedure is a key point. Okay, that's all for my introduction. Thank you very much.
Very much, Professor Feng. And now we have some minutes for questions.
Zoltán, yeah, Zoltán is raising his hand. Yes.
So we have Zoltán. Please go ahead, Zoltán.
Thank you very much. Excellent presentation. Very interesting. Just a quick question on are you planning to actually use this as a tool to assign value to a CRM? So is in China developing transferrin or hemoglobin reference materials?
As far as I know, we did not have the matrix CRM, hemoglobin CRM. Maybe we do not have, but in the next step, we just use a developed method to develop the CRMs.
I understand.
At present, maybe the purity CRM we have.
For these proteins.
Yeah.
I understand. Okay, thank you very much. Congratulations. Thank you.
We have more questions.
Yes.
Yes.
Yeah.
So
it's probably me. So Bernd Güttler, thank you very much for this very interesting talk and a very valuable contribution to clinical chemistry. And this is an issue which has been widely discussed in the past, and it is very important to have a reference method here. And my question is related to the investigation of whole blood. How do you ensure the homogeneity of the samples?
Homogeneity of what? Yeah, sorry.
The homogeneity of the samples when you have whole blood and you also you send samples around. It's much more difficult to handle than serum. So maybe you can tell us a little bit about that.
Sorry, I did not consider the homogeneity of the sample because we just use a blood sample, and after centrifuge and the pre-treatment, we just use the method to develop the method, just use the sample to develop the method. And the next step, when we develop the CRMs, maybe the homogeneity is the most considering case. Yes?
Yeah, okay, thank you very much. It's a very valuable. Thank you.
Thank you, Bernd.
And I think we have also one more question, please.
Yes.
Yeah, sorry, it's Gavin O'Connor here from PTB.
Yeah,
sorry, I only came into the last part of your presentation, so I didn't see it all. I've got a question about the engagement with the community. So total hemoglobin as required by the community is based on the cyano method, which measures all heme-containing iron. And we've engaged quite a lot here at PTB in measuring species-specific hemoglobin. And we now have confirmation from the community that they measure the heme-containing component from blood, not total hemoglobin. Therefore, we've got a big uncertainty on the definition of the measurand here. And if we don't engage with the community, we may have very, very accurate and precise methods for measuring total hemoglobin, but it's not what the community uses, even though they call it total hemoglobin. So what work are you doing with the community to get these more accurate measurements accepted within the hematology community?
Yes, thank you very much for your question. It's a very good question because, as we know, the hemoglobin has several species. Yes. So in this work, in this paper, actually, I don't think it is a communicability study. We just use a clinical used method to measure the comparison. Maybe the merit, we just define the merit. I remember a CCQM comparison just maybe last year or the year before last. We just use HGB in blood measurement. Under the ICP mass method, the results from several ICP mass method a little bit lower, just because of the HGB species. I totally agree with your comments. And in the next step, we just want to research carefully about the species, because different species maybe use ICP mass strategy. We can get different results just because of the merit definition. Okay.
Thank you very much.
Thank you.
Do we have more questions? No, I don't think so. So thank you very much once again, Professor Feng.
Thank you very much.
So the third presentation today is on an SI-traceable reference material for virus-like particles. Is a combined team from BIPM and NPL, and the lecture would be delivered by Andrea Briones. Andrea joined NPL in 2017, focuses on applying innovative methods and methodology to address challenges in antimicrobial resistance and synthetic biology. Her current research focuses on applying analytical and biophysical methods for the study of materials, physicochemical properties. She spent 18 months at BIPM, and the study which was awarded, or the paper which was awarded and which will be presented today, is a result of that time spent at BIPM. And Andrea is also leading a project at VAMAS related to this SI-traceable measurement of virus-like particles. So, Andrea, the floor is yours.
Thank you so much, Zoltán, for the kind introduction. Just bear with me that I share my screen. Thank you for the award, and I'm very pleased to be here in this presentation and take you through our work. As Zoltán kindly mentioned, this is a work in collaboration between NPL and the BIPM, where I spent a beautiful 18 months over there learning a lot of stuff. So yeah, I'll get started with the presentation. So first of all, here is the outline of the presentation. I have divided this presentation into 5 main sections. The first one is metrology for engineering biology. Then we have quantification of intracellular delivery by virus-like particles, followed by the presentation of the first traceable reference material for VLPs, the impact of this work for gene therapy, and the traceability chain for the measurement of the virus-like particles. So, first of all, to start with some introductions, what is engineering biology? At NPL, we are establishing a measurement framework for engineering biology to support synthetic biology and biomanufacturing processes in cellulo and in vitro. What you can see in here is a cartoon representing the areas that are either already established at NPL or they're in progress. You have cell-free systems, you have VLPs, you have DNA synthesis and cell work. These are high valuable applications. For instance, for advanced therapies, cell-free, cell-based production platforms, DNA, RNA, and vaccines. But particularly for this presentation, I'm going to focus in the VLPs. And this can be applied for diagnostics, antimicrobial resistance, and most important, which will be the focus of this presentation, gene therapy. So I would like to introduce you to the impact of our work. We believe our work can have or has already a great impact in gene therapy. In here, I'm showing you a slide with an example of what is in vivo and when we have ex vivo gene therapy. Just bear with me to get rid of this bottom thing that doesn't let me see. Okay, great. So in vivo, for instance, on the left is when genes are changed in cells when the cells are still in the body. And to the right, we have cells are modified outside the body, and these are transplanted back in again. So at the middle of these both systems, I have placed our VLP, and at the core, at the heart of this VLP, I have placed the SI units, because our material has been characterized all the way to the SI units. And we believe that gene therapy can highly benefit from this. I haven't read anything in the market at the moment or any publication saying that there's a reference material for this kind of work. So, again, to continue with introductions, what is the relevance of virus-like particles? Number one, for vaccine development, you can see in here the cartoon that the exterior of these VLPs can be decorrected with chemical coupling, peptide conjugation, genetic fusion. Number 2 for gene delivery, and will be the focus of this presentation mainly. Our VLPs are hollow, therefore these VLPs can be packed with DNA or RNA. And third, for antimicrobial, because our designs are special and they can kill bacteria on contact. So these VLPs have many, many applications. Right, so what is methodology for engineering biology? Engineering biology applies engineering principles to the design, redesign, and repurpose of biological systems at the primary component level, being genetic, protein, bio, and macromolecular assemblies. What you see in the right is our toolbox. NPL, we have this concept of the toolbox, which should be populated one day with a number of RMs. So as a result of these great efforts, we have just published last year the first SI-traceable reference material for virus-like particles. What you can see here on the left is a representation of this. At the bottom, you can see a virus-like particle, and the virus-like particle is made of a number of triangles, and each triangle represents a monomer. And at the top, you can see that we have characterized this monomer, and we have made it the SI-traceable reference material. To the right, you can see the design of the peptide of this triangle, let's put it that way, which we call the triskelion. And at the bottom, you can see this peptide, once it is mixed in a buffer of biological conditions, let's say pH 7.4, it has the ability of forming MD VLPs, which is great. And I will explain more about this in the next coming slides. So in here is our material. It's called a triskelion. And what is a triskelion? As I just explained briefly, this is our triskelion. It's a peptide which has a little white core in the middle, and attached to this white core we have 3 blue arms, and each blue arm has these red parallel strands. As it stands, it's called a triskelion, and it's a monomer able to form virus-like particles. Now, I want to highlight that when I went to the VIPM, I did not take the triskelion itself, because to characterize something that is constantly changing, it would be a little bit difficult. So what I took was the triskelion minus these red things. It will result in something similar to this, which means it remains a monomer, but is unable to form virus-like particles. And it is called actually the C3 hub, but for the sake of the presentation, I will refer to it as a triskelion, whether it is like this or like that. It would just make things a lot more simpler to explain. Here, I'm zooming and highlighting one of the arms of our C3 hub. You can see the sequence in there. So in here is the paper in question. We are very grateful for the award. And to the right, you can see the workflow. So when I arrived to the BIPM, I arrived with 1 gram of my material. All right. I'm not going to spend a lot of time in these slides, but very briefly, when I arrived there, we said, okay, we need to characterize this. We need to check the max fraction of the triskelion in the material, the actual purity in milligrams per gram. So we passed this material through the mass balance method, high resolution LC-MS, amino acid analysis, qNMR. COVID happened. It took some time, great efforts, but we did it. And at that point, we actually thought, okay, so it looks like things have worked. The uncertainty is not too large. Seems that it's okay. So we started to actually think, so okay, it can be a primary reference material, and eventually maybe it can be used for higher order reference procedures. Let's say for a transfection experiment where people are transfecting with VLPs, and therefore we could use it for that. And I will explain this concept a lot better in the next coming slides. So just to finalize with introductions, when I went to the BIPM, we mainly use these methods. The mass balance, which is a summation of impurities, is very robust, has a wide applicability, small uncertainties. It does take time, and you need to use a lot of equipment. Then we have what we call the more simple primary methods, like qNMR and amino acid analysis. Now, it is important to highlight that both approaches need to be corrected for structural impurities by LC-MS, and I will explain why in the next coming slide. So this is a nice table, which, to be honest, I took from one of the papers with the BIPM. This very nice table is called SI-traceable peptide purity value assignment approaches. From left to right, you have the mass balance method, where you can check for water content, volatiles, non-volatiles, counter ions. Then you have PICA, where we take our peptide and we're going to hydrolyze it, we're going to separate it and quantify by LC-MS. Then we have QNMR and we have elemental analysis. Again, I need to highlight that it is important to separate and quantify the structural impurities by LC-MS. And why is this? Because, for instance, if I'm doing PICA and I'm hydrolyzing my sample, inside this sample, I have my triskelion plus structural impurities, very possible, right? So the first thing I have to do is to pass my sample through the LC-MS, separate the structural impurities and quantify this. And let's say that after quantification, I say, okay, I have X amount of structural impurities and these are, I don't know, 5% maybe. So then after I perform all these experiments in here, I will correct this data for 5%, okay? So in here you have relevant peptide biomarkers that have been studied by the BIPM, and they have gone through these methods, which are very well established. So to finalize with the paper, actually, we have this nice table. As I mentioned at the beginning of the presentation, I arrived to the BIPM with 1 gram of the peptide. And out of the 1 gram, we actually had 669 milligrams of the peptide. And the rest was mainly water, TFA, and cations. So at this point, we said, okay, we managed to succeed at the BIPM. We characterized very beautifully, chemically, this VLP. What's next? What can we do with it? So this is where the next slide comes in. We had to find a purpose, a scope for our work, how to carry forward this. So this can be a tool for comparison of biological measurement results worldwide. It's a unit of measurement, a biological system, support harmonization for international regulations, for use by regulatory authorities and manufacturers. Now, thinking about that, I prepared this next slide and I titled it Traceability Chain for the Measurement of Transfection Efficiency. If we have a look at the right, I have prepared a simplified measurement traceability pyramid. At the bottom of the pyramid, we have our scientists, our customers who are performing measurements, who are performing research. And let's say we have this scientist, he or she's into VLPs, and she wants to actually quantify how successful was his transfection experiment. So in order to quantify anything, we will need of a standard of an RM. So this is where our material becomes very useful because we don't see any reference materials for VLPs and for these sort of experiments. So on the left, you have a schematic of a transfection experiment. At the top, you can see your VLP, which has been packed with your DNA. It will be uptaken by the cell. The DNA will be released. The DNA will go to the nucleus. The reaction will happen and you will have your product. Until the point is great, the scientists can tell maybe it worked, maybe it didn't work, but how do you know how well it worked? How do you quantify? So let's say this experiment was performed in HeLa cell lines. So what I do, I take the actual monomer of the triskelion, not the fully folded VLP, but the monomer. And then I prepare a nice standard curve in HeLa cell lines. And then using the same methods, I will pass my transfection experiment. Now, what I'll be fetching in the LC-MS will be for the transfection agent. Usually it's a VLP. It could be any VLP, or it could be also our triskelion form VLP, but it doesn't matter. And based on that, I will be quantifying by comparing with my standard curve, which was done in the same HeLa cell lines. And I will show this in more detail now. But before that, I want to show you that we have identified some challenges in these fields. Number one, the first methodological challenge is the actual vector. We need to characterize it very well before doing any transfection experiments. This has mainly been done with the great work we perform at the BIPM. Then number 2, we have encapsulation, because once we are packing our VLP with some DNA, you're not sure if it has worked. Maybe you have 100% fully packed and loaded VLP. Maybe you have an empty VLP. So this is quite important. Then number 3 is the work which I'm performing right now, which is the quantification of peptides post-transfection. And I have a VAMAS call open as well, which I will show it to you later. And number 4 is the activity. So now going back how I am quantifying. Okay, this is just the very simple schematic of what I am up to, because as you can see, it's a very new field and I'm trying to do new stuff in here. Number 1, as I explained before, we have our transfection experiment in cell lines. Number 2, I will prepare my standard curve in the same cell lines where the experiment has been performed. And number 3, I'll be quantifying by LCMS. And I will explain here a little bit more what I'm getting. So the first thing I had to do is to check that indeed our triskelion could be seen in a complex biological matrix. It's not that easy. So in this way, I could be linking the actual data from the transfection experiments to the SI unit. So I selected the LCMS because it's the instrument that I use most. And the first thing I did, I prepared a control to relatively high concentration in water because I wanted 0 background. I set up my LCM method. I saw a nice peak. And then I actually checked which masses were belonging to this peak. And at the bottom, you can see these masses are the ones from the triskelion. And then using the same LCMS method, I passed some triskelion, which was in some cell extracts or cell lines. Then I saw this peak slightly shifted, but I still got a nice peak, which area I can measure for quantification actually. So I said, okay, it's not too bad. I had a look at the masses, and these masses also are the ones from the triskelion. Therefore, it proved that indeed our material can be used in transfection experiments, can be used in complex biological matrices, and the LCMS, it is a method that can help you to quantify. Now, on the left, you can actually see all the background coming from the actual cells, which is overwhelming, but still, I can still see our triskelion, which is great news for the application of this material for the scientists to use. So as a result of that, we opened this VAMAS call, which is called International Round Robin on Post-Transfection Peptide Quantification and Reproducibility by LCMS. Please, if you want to form part of this, just send me an email. I'll be happy to send you more information. I am currently writing this protocol, so it's not quite ready. So you wouldn't receive any samples until the end of the year or beginning of next one. But it will be great so that we can check if this work is actually working really, if we can use it for transfection experiments. And this is it from me. I'd like to thank you for having me here. Thank you for listening to me. To thank BASE for funding my work, industrial strategy, the BIPM, and VAMAS. Thank you very much.
Thank you very much, Andrea. And the conference is open for questions and comments. So maybe I would start off. So what are the next steps? So after the VAMAS study?
The next steps after the actual VAMAS studies, well, I'll send the samples. I hope that the actual data is not too actually bad, because if it is bad, then I cannot go forward very much. It means I need to go backwards and optimize everything and then restart the VAMAS study. If it works, it'll be extra information and confirmation that our triskelion can be used and it should be official on RM. That'll be the next step. And then we will follow and jump into a new RM and so on and so on.
Mm-hmm. Thank you.
Mm-hmm.
Any other questions or comments? Please just unmute and speak up. If not, I would like to thank you, Andrea, for the excellent presentation, and I would like to invite all of you to come back on camera, and we would take a family photo here. And in the meantime, I would like to thank all of our speakers and my CITAC colleagues to actually organize this award symposium and actually operate the award. And I would like to invite all of you to consider your upcoming papers and your colleagues' papers to be nominated for the next round of the award. The cards would be going out towards the end of the year. So keep an eye out for it, and even if you don't see it, just reach out to somebody at CITAC and propose your papers. So thank you all of you joining us today, and looking forward connecting with you probably face-to-face a year from now for our next round of CITAC meetings and award symposium in 2024. Thank you very much. Goodbye.
Thank you. Bye-bye.
Thank you very much.